Two black holes, each about 30 suns each mass, rushed together until space itself buckled. Hear this bowl. One clear note, then a thinner overtone riding under it. Black holes do that in gravity. We just heard the cleanest ring down yet sent across space and time to our detectors. Two tones from a newborn black hole. Those notes told us its mass and its spin, and the area of the horizon got bigger, exactly like Stephen Hawking said that it must. 10 years after the first wave detection, instruments are now quiet enough to separate these notes and give us this physics confirmation. That's the story today. I'll show you the wave, the tones, and why this matters. Years ago, on September 14, 2015, LIGO heard the first gravitational wave, GW1 50914, after a 1.3 billion year trip across the universe. That moment gave us a new sense. We could hear space-time itself. Since then, the LIGO, Virgo, and Kagra gravitational wave detectors have caught dozens of signals from black hole collisions, neutron-star mergers, and rare mixed pairs. This is cutting-edge experimental astrophysics in action. Today's milestone is louder and cleaner. The event is called GW2 50114. Two black holes, each roughly 32 times the mass of the Sun, collided. The signal was so strong, it let the team test classic theoretical predictions from Einstein, Hawking, and Roy Kerr with unusual clarity and accuracy. First, the basics. Einstein's general relativity said space-time carries ripples of gravity. That is what LIGO measures. LIGO stands for Laser Interferometry Gravitational Wave Detector. These detectors are so precise, they track changes in laser beams that are only 1/10,000th the width of a proton, about 700 trillion times thinner than a human hair. When the lasers are disturbed as a gravity wave passes through the Earth, we get a signal like GW1 50914. That sensitivity took decades of invention and a lot of patience. GW 250114 stands out because it is loud. Loud means clean. Clean means you can isolate the ring down tone. The moment the newborn black hole relaxes and sings, think of a struck bowl. The pitch and the fade rate carry information like the black hole's mass and spin. Now the two big checks. Check one is Hawking's area rule. When black holes merge, the total event horizon area cannot shrink according to predictions. For GW 250114, the team compared areas. Before the smash, the two horizons together had about 93,000 square miles of surface, roughly the size of the UK. After the smash, the new horizon had about 154,000 square miles, about the size of Sweden. Larger. Score one for Hawking and Bekenstein. Boundaries of no return do not get smaller in these classical processes. Check two is Roy Kerr's prediction for rotating black holes. A finished black hole is fully described by two numbers, mass and spin. Nothing else survives. If that is true, the ring down should contain tones that line up with those two numbers. GW250114 gave us the cleanest version yet. The team pulled out not just the main tone, but a second tone, two notes. With those, they read the mass and spin from the ring down and compared them to the mass and spin inferred from the earlier part of the signal. They matched within the errors. That is strong evidence that the object is a plain Kerr black hole. No extra hair, no hidden structure sneaking in. Why does this matter? Because it shifts gravitational wave astronomy into precision mode. Patricia Schmidt put it clearly. Detecting a system like the first one, but 3 times louder a decade later, is what you get from regular, purposeful upgrades. Quieter lasers, better mirror coatings, sharper calibration. The instruments in Washington and Louisiana can now measure distortions at a scale most people would call impossible. Famous physicist Kip Thorne admitted he once doubted this could work. In the 1970s, he thought the needed noise reduction was out of reach. It took years of thought and a lot of invention to make LIGO real. It is real. It works. And it just gave us the clearest look yet at how black holes behave. Let's put the physics in plain terms. Two black holes spiral. The chirp tells you their masses and spins as they dance. Then the crash and the newborn black hole rings. Those tones carry a second, independent path to the same numbers. If the two paths agree, the object is what general relativity says it is. If they disagree, and the effect survives, rechecks, that is news of the disruptive kind. There is also a celebration of scientific progress. On September 14th, 2025, LIGO marked 10 years since that first detection. What started as a whisper is now a shout. The collaboration has logged black hole pairs, neutron stars, and the odd black hole neutron star couple. Each one adds to a new catalog. With a bigger catalog, we can map how mass and spin are distributed, and we can look for subtle shifts in tones that track environments. Einstein predicted gravitational waves, but suspected nobody could ever measure them. The National Science Foundation backed the long game anyway. The result is a new window, a new sense of the universe. Amir Ali said it well. We are just getting started. More detectors are coming. A fourth site in India is planned. The more ears we have, the better you can pinpoint where a signal came from and the sharper the tests get. Let's be honest about what this event did not claim. It did not find new forces of physics. It did not break general relativity. It did not show quantum hair. What it did was better. It confirmed Hawking's area law with clear numbers. It confirmed the Kerr description with two tones from the same ring down. It did this at a precision that comes only from a very loud signal and very quiet instruments. If you want a yardstick, compare the areas again. UK before, Sweden after. That is not a metaphor. Those are the order of magnitude surface areas of the horizons involved. Big clean numbers, easy to remember, even better to test. So, where could this lead? Toward a bridge with quantum gravity, the holy grail of modern astrophysics. Horizon area keeps acting like entropy. Entropy counts microscopic states. The more events like GW 250114 we analyze, the tighter that bridge gets. No wild promises, just a clear path. More signals, cleaner ring downs, stronger tests. As humanity pushes, it senses out into the farthest reaches of space and time. It's becoming clearer that the more we invest in this exploration, the greater our understanding. Black holes, to most physicists, are the key to understanding the deepest levels of matter, space, and time, to finally unifying the quantum world with gravity, to knowing ourselves and our place in the cosmos.